Hello, and welcome to Cognitum, a show dedicated to exploring the present and future of science and technology. I'm your host, Iosif Gershteyn. Today we have in the studio Dr. Andrey Vyshedskiy, a professor of neuroscience at Boston University, theorist, and entrepreneur. He is here to discuss the core ideas in his wonderful book, The Origin of the Human Mind. Hello, Andrey.
Hi, Iosif. How are you?
Very well. So what drove you to create this theory?
Well, it's a long story. I've got interested in how brain works since I was 9 years of age, and I've been reading everything that came along the way. And at that time, I was particularly interested in telekinesis and telepathy. And that kind of kept my interest going. And at some point, a friend of mine, Michael Levin, he's now professor at Tufts, he asked a very simple question. If telepathy really exists, and if it exists in animals, why then evolution didn't work its magic on telepathy so that telepathy would blossom and become really the channel for communication between animals? And so the only possible answer to that was that telepathy didn't exist in animals. It's really human beings, us modern humans, are the first species that that have something in our brain that enables telepathy. And I was looking in that direction, and that kind of put me onto the question of evolution of the human mind. And I started, it started 25 years ago. I was looking into this question, and I realized that we don't really understand how the brain evolved since we split from chimpanzees 6 million years ago. We understand a lot of pieces, we have a lot of archaeological evidence, but we don't really understand what was going on inside the brain. Because, as you know, the brain of a chimpanzee and the brain of a human look very similar. It's just the size. Our brain is 3 times bigger than the brain of the chimpanzee.
So wouldn't the natural question be, is it just the size difference that caused this change and caused the evolution of the human mind?
And a lot of people thought that it is just the size, but there are several lines of evidence that really not in favor of that hypothesis. Some brains are really large. Usually people bring up the brains of whales and brains of the elephants. These brains are many times bigger than the brain of a human. The evidence that really convinced me was people who lost half of their brain in their childhood. There is a gentleman who discharged a gun into his right hemisphere and lost half of his brain when he was a child. And later on, he graduated college with honors and have normal cognition.
So a young man put a bullet in his head, which disabled half his brain, and he was able to be normal cognitively.
That's right. That's right. So it really cannot be just the size. Of course, the size matters, but it cannot be just the size. It has to be something else.
So what is that something else?
Well, there are plenty of theories, and people were pondering that question for a long time, for thousands of years, right? Humans are definitely cognitively different than other animals. But every time you kind of focus on one thing, you encounter a lot of problems. People were focusing on the theory of mind, And there are plenty of publications that are in favor of differences in theory of mind, and a number of recent publications that kind of saying that this is not really the case. Theory of mind exists in chimpanzees.
Pardon, could you quickly give a synopsis of the theory of mind?
Right. Theory of mind is my ability to understand what you are thinking about.
So its ability to imagine someone else's headspace.
That's right. And there were many other theories. Darwin was thinking, for example, that it is language, the ability to produce articulate speech, that really separates us from other animals. But since 150 years ago, when Darwin was talking about this, we now know that we can teach chimpanzees and other apes plenty of words, hundreds of words, and they understand those words. They can sign those words or use lexigram to communicate those words. So words are really not a problem. It's something else. And nowadays, most people are, not most, I shouldn't say most people, but a lot of people are looking at the imagination. But again, this is where confusion starts, because imagination is such a neurologically broad thing. And this is where I came in with my theory and tried to use neuroscience. I'm a neuroscientist by education. Try to use neuroscience to delineate different types of imagination. And this is what theory is about.
Could you introduce us to your theory?
Absolutely. So maybe we should start with different types of imagination. Because people, both lay people and scientists, they use communication to describe multiple phenomena that are occurring in our conscious experience. For example, if you have a dream in REM sleep, weird, bizarre dream of you flying over town, that is, of course, imagination. But that imagination is very different from the purposeful, conscious imagination that you use, for example, to imagine an apple on the back of a dolphin. The dream was created spontaneously by neural ensembles in your posterior cortex.
Pardon, could you describe what a neuronal ensemble is?
Right, sorry. When we store our memories as ensembles of neurons. Well, the brain, of course, consists of neurons. We have 86 billion neurons in our brain, and the top part of our brain is called cortex, from the Latin word for bark. Like tree bark, cortex looks like bark and is on the outside of the brain. And these cortex enables mammals. All mammals have cortex, pretty much similar to what humans have. This cortex enables us to remember any new information. Humans are visual creatures, and so most of the examples would be primarily visual. So cortex enables us to store this visual information, new faces, like I saw you and I remember your face. I remember people I've seen before, I remember the object, I remember the different car models. I remember all kinds of abstract pictures in my cortex. This memory is encoded by groups of neurons that are connected to each other. These connections make those neurons to fire together. So the idea is, it's really a Hebbian, what we call Hebbian principle. Hebb, H-E-B-B, was a scientist in the 1950s who first introduced the concept that neurons that fire together, wire together. So when I look at you, I see your eyes, eyebrows, nose, lips at the same time, and my neurons are firing in synchrony. When they fire in synchrony, they create the connections between themselves. And these connections consolidate over time into long-term memory, and this is what we call neuronal ensembles. Neuronal ensembles, other people call neuronal ensembles neuronal assemblies, and they call it multiple different names, but I prefer neuronal ensembles.
So these groups of neurons that are distributed in the brain, but they fire together, how is it that they fire together at the same time when they're in different areas of the brain?
Right. Well, you're absolutely right. These neurons are distributed all over the posterior cortex. They're not in one small place. A neuronal ensemble of your face is encoded in multiple regions. The colors are encoded in one region, and the forms are encoded in other regions. These neurons are connected by synapses. That synapse is a connection between any two neurons. But the neurons of a neuronal ensemble, they have stronger synapses between them. And when part of the neuronal ensemble fires, the other part fires as well. So the neurons of the neuronal ensemble have a so-called resonant ability to fire as a group. And when they fire, they create an experience for you of the object that they encode. So if now I ask you to imagine an apple, millions of neurons in your brain will fire up simultaneously and will create the experience of apple to you. The color of the apple, the shape, the texture, maybe the smells of the apple, all of this will be created in your mind because millions of neurons encoding this apple will be firing up at the same time.
Well, this sounds a little bit like a small miracle. You know, you say, imagine an apple, and all of a sudden millions of neurons fire simultaneously, and these neurons are distributed in the brain in different areas. Now, is there some control mechanism, some single neuron that sends the signal to all these disparate parts to fire together, and it recognizes apple? Or how does that process work? Because, or does each one of these million neurons react to your word, imagine an apple?
Right. Well, it's definitely a miracle. And it's a miracle that not just humans possess. It's a miracle that probably most mammals possess. You say a word, and if your dog knows what that word means, probably your dog would imagine that object. Neurologically, how it works, we understand it in general. We may not understand the details, but we know that the words are associated with the object, with visual objects, can be associated with visual objects. And when word is spoken, you hear the word, you match it to the library of words stored in your brain, and then the associated image pops up through multiple connections. It's never one connection. It's always multiple connections between different areas that enable the image of the apple to pop up. But the idea is that it's not the one neuron, a few neurons that encode the apple. The idea is that millions of neurons that encode an apple will pop up and create the visual experience for you, the perception of the apple.
And how specific are these neurons? That is to say, when I think of a red apple, how many of those same neurons are going to fire when I think of a red Corvette?
Right. These neurons are somewhat specific. but the tuning of these neurons is never very narrow. They're broadly tuned. So the red apple and the red corvette would have some overlap in the area of the brain that encodes color. It is very likely that some of the same neurons encoding red color would fire both for the apple and for the red corvette.
So there is a level of abstraction that happens to allow for infinite perception.
Definitely. You can store infinite number of objects reusing the same neurons and probably reusing the same parts of objects. Some of the lines will be reused for multiple objects.
So your refined understanding of imagination, how does that play into your theory? And could you give some context and a better understanding of the actual bones of the theory?
Right. So until now, we've been only talking about the objects, and the objects are the basis of our thought processing. But then the question is, what can you build out of these objects? And we discussed several types of imagination. We discussed the dreams, when these objects pop up into our imagination spontaneously. Probably because we've been thinking about these objects consciously or subconsciously when we've been awake. Now objects pop up into imagination during our sleep and create a new movie. This is not the imagination that is unique to humans. This is imagination probably possessed by most mammals, because most mammals have dreams. The unique imagination unique to humans is the imagination that is controlled by the lateral prefrontal cortex, but this part of the brain just behind your forehead on the side, particularly left lateral prefrontal cortex. That is the part of the brain that has a remote control of the films. That is the director of the films that you can watch when you're awake. This part of the brain is inactive during the sleep. So during the sleep, the objects pop up into your consciousness spontaneously. But during the day, when you're awake, the left lateral prefrontal cortex is mostly responsible for creating the movie for you that you watch during the day. This is the part that allows you to imagine new images, like an apple on top of an elephant, or imagine this chair on top of this table, or you can imagine yourself jumping up and down and decide whether it will be good or not. This is the part of the brain, the left lateral prefrontal cortex, that creates this new experience in your mind by invoking and then synchronizing the neuronal ensembles.
Do you happen to know
if
it's active during lucid dreaming?
Yeah, that's a good question. I've been asked a lot about lucid dreaming. It's popular recently. Yes, so lucid dreaming is different from the non-lucid dreaming by the activity of the prefrontal cortex. So when the lateral prefrontal cortex is completely off, you have no control over your imagery. But when the prefrontal cortex is a little bit active, maybe not as active as when you're trying to multiply two-digit numbers, but slightly active, you can use your lateral prefrontal cortex to control the content of your experience.
So when you have more activation of the lateral prefrontal cortex, especially on the left side, you have more control over the images. that you see or that you direct to see.
That's exactly right. That's exactly right. The left lateral prefrontal cortex is your control center for both recall of images and, most importantly, for synchronization of images that you use in this purposeful, conscious type of imagination that is unique for humans. And maybe it is time to actually define that type of imagination, because if we don't define it, I will be continuously using this long phrase, purposeful, conscious, unique imagination. I came up with the name for it borrowed from psychological papers that were published several hundred years ago. I call it mental synthesis. The idea is that you, just like proteins are synthesized out of amino acids, you synthesize your thought out of objects, out of separate images, and therefore we call it mental synthesis. So mental synthesis is the purposeful, conscious imagination that is probably unique to humans.
Mm-hmm. And what are the implications of having this unique ability?
Right. Well, there are many implications. Some implications present interest in terms of development of children, and these are probably the most interesting implications. Some of the implications are relevant to evolution of humans, and they allow us to speculate how our ancestors evolved from chimpanzees, and that's how we started this conversation. And other implications are theoretical, how the brain works, what is the neuroscience, neurology of our imagination. So which one do you want me to start with? The children, evolution, or the neurology?
Well, let's start from the neurology and then work our way backwards.
Very good. So in terms of neurology, to enable mental synthesis, we had to jump a certain number of hoops. And the problem is that to be able to create novel image, you have to synchronize the parts of that novel image. So you recall images stored in your memory, and then you have to synchronize them, right? Because if you just recall them, if you just recall an apple and then recall a dolphin, those would be two different things, an apple and a dolphin, right? If you want to really imagine an apple on top of the dolphin, you have to do something else. And this something else is probably synchronization. So your left lateral prefrontal cortex have to synchronize millions of neurons that encode your apple and millions of neurons that encode a dolphin. And this is not an easy task. It feels easy because we're so used to it. But it's not easy in terms of neurology, because the distances to these neurons are different, right? The distance from the left lateral prefrontal cortex to some part in the left temporal cortex is much shorter than the distance from the left lateral prefrontal cortex all the way to the right parietal or right occipital lobes.
But how tight are the time frames? I mean, the distance, the deltas in the distance seem to be so small that the level of synchronization has to be very high for that to have an appreciable effect.
You're right. We were probably talking about gamma rate synchronization, where we have just a few milliseconds, a few thousandths of a second precision that we need to achieve for the apple and the dolphin to be in the same conscious frame, so you experience them as the one and the same new object.
So
a few milliseconds.
2, 4, 5, something like that?
Yeah, 2, 4, 5 milliseconds.
2 to 5 thousandths of a second is the precision of accuracy, is the precision of synchronization that has to happen between wildly disparate parts of the brain to fire at the same time.
That's right. And if you just look at the identical axons, in the identical connections between the lateral prefrontal cortex, left lateral prefrontal cortex, and the parts, distant part of the brains, you will see the difference in distances that are tenfold, or maybe even 50-fold. So what has to happen?
So if they traveled at equal speed, how tight would the synchrony be?
If they travel at equal speed, the differences would be tens or maybe hundreds of milliseconds. So definitely they will not be synchronized.
Orders of magnitude.
Orders of magnitude different.
Mm-hmm.
What has to happen is that these networks that connect the frontal part of the brain with the distal part, with the posterior part of the brain, they have to be synchronized. They have to be synchronized in respect to the left lateral prefrontal cortex. And once that synchrony is achieved, then the left lateral prefrontal cortex can synchronize disparate neural ensembles and create this absolutely fascinating ability for us to imagine anything we want. Mm-hmm. And this really brings us to the question of how children establish that synchronous networks. Because you are not born with these synchronous networks, right? Nor do you, if you just take a child and put the child into an attic until the child reaches puberty, that child will not be able to establish synchronous networks. And the child would have real lifelong consequences. That child will never be able to understand spatial prepositions. The child will never be able to use mental synthesis to understand to understand novel images that you describe. Basically, we usually refer to these children as low-functioning children. Of course, there are no prospects for any kind of job because the child would not be able to understand normal conversation.
So developmentally, when this process of maturation, of being able to synchronize these disparate parts of the brain from the left lateral prefrontal cortex, that's when, if that development is interrupted, then the child cannot develop imagination, therefore cannot cognitively mature.
That is correct. That is correct. And during the development of children, there is intricate play between the use of language that the child uses not just for communicating with other people. The children use language also to train their imagination, to train their mental synthesis. Children talk to themselves. They imagine novel scenarios in their mind. I remember my younger son was imagining how, when he was 3, he was imagining how he would protect our house from invaders. So he knew very few words. He maybe knew 100 words at that time. But he would go on and for hours describe how would he build defenses. He would put trenches here and tanks there and soldiers here to protect the house from invaders. So that was, he was using language to imagine novel images, novel scenarios in his mind. And in that process, he was training his network to be synchronous, and we haven't mentioned that the synchronicity is established by layering myelin on top of the axons that can change conduction velocity between the axons. So the axons that are nearby can have fewer layers of myelin, and axons that are far away can have more layers of myelin and therefore have greater conduction velocity.
So for these children that are damaged, that that have this developmental issue, this problem. What is the implication of your theory, and what are you doing about it?
Right. So most of children who are likely to have this problem, we now refer to them as kids with autism, not just with autism, with low functioning autism. Unfortunately, you don't really know who among the children will end up high functioning, who will end up low functioning. So we, as a society, now understand that it is absolutely essential to enable these children to use language. Not just language, but full language, syntactic language with spatial prepositions and verb tenses and syntax to enable these children to use language to train their networks. Now, let me give you an example. Until 1990s, since 1990s, all children in the United States are tested for congenital deafness. And this is mandated by the state laws. What's the reason for that? The reason for that is that we realize that it is absolutely essential for the children to be introduced to full formal sign language from as early as possible. Well, the same idea works for kids with autism. We need to introduce these children to full language as early as possible. These kids don't learn language like typical children. Typical children will pick up and soak this language, soak words, and will use the words to both communicate and drive their internal imagination, internal scenarios on their own. 70% of children with autism don't do that. They don't pick up language. They have to be specially introduced to words, convinced to talk. And still 30 to 40% of children with autism unfortunately remain low functioning for the rest of their life. And I hope with what I'm doing now to change that number, to maybe reduce that number with multiple tools that teaches children elements of language, both words and, most importantly, imagination, mental synthesis.
And the name of your company and the app that you have developed?
Right. Well, that project was incorporated to separate it from myself as Imagination. Imagination is the company that we started 5 years ago with the idea of producing tools for children with autism, children who don't spontaneously acquire language. Imagination developed several tools. The most used tool is called Mental Imagery Therapy for Autism, abbreviated MITA, M-I-T-A. And MITA uses both visual exercises and linguistic exercises to promote internal imagination, to promote mental synthesis. It's kind of puzzles, so brain teasers, and they make children to use their own brain, to use their left lateral, to solve those puzzles. You have to synchronize neural ensembles in your brain. To synchronize them, you have to turn on and use your left lateral prefrontal cortex.
So this trains the brain working around the problem which affects autistic kids, which is delayed language learning.
Yes, the idea is that even people who cannot say any words, they still can use that product to develop their mental synthesis and therefore have a basically break the mental synthesis barrier. And there are plenty of articles that show that once you acquire mental synthesis, you really open up whole new territory for learning. The learning jumps in every direction, because you understand conversations, you understand fairy tales, you understand what we are talking about.
Thank you for joining us tonight with Dr. Vyshedskiy. It's a continuous wonder to see the fruits of human ingenuity benefiting society and the individual. We hope you join us again next time.